To begin this lesson, let's take a look at something that you might have already learned in a science class. That if I'm looking for the position of a function at time t, we might assign that function s. So position is s of t. Now, if I want to find the velocity of, let's say, a particle moving with position s of t, the velocity would be the rate of change in the position with time, or in other words, s prime of t, the derivative of position. And then we can talk about a term called acceleration. And what acceleration is the actual change in velocity with time, or the derivative of velocity. So the first derivative of velocity is essentially the second derivative of position. And it looks like that. If we call this v of t, velocity, then position, of course, acceleration would be v prime of t, the rate of change in velocity. Of course, you probably have learned this at some point in a science class, maybe not with this notation, but now together with your knowledge of derivatives, this should be pretty straightforward. So now here in example 1, we have a velocity graph. So we will say y equals v of t. Now remember, since this is a velocity graph, it is the derivative of something. In this case, this is a derivative graph of the position. Part A asks, at what time on the interval 0 to 8 is the particle standing still? Well, we're going to just answer the question. The particle is standing still at t equals 3. Now, why is the particle standing still at t equals 3? Well, that is because the velocity of the particle is equal to 0 at this time, t equals 3. We'll ignore units here for a moment, but you can see visually at crossing the t-axis, it is the 0 of the velocity function. For the sake of developing the concept, let's assume that this velocity graph has open circles. I know the graph presented has closed circles, but let's make them open so we only consider t values on the interval 0 to 7. Let's not worry about what is happening at those particular endpoints. Part B asks the question, when is the particle moving to the right? So the idea here is the particle is moving to the right when the velocity is positive. And if we look at the velocity graph, positive literally means above the t-axis. So here, v of t is positive, and when it's below the axis, v of t is negative. So to answer the question, the particle is moving to the right when t is an element of the interval 0 to 3. Now the reasoning for that is because v of t is greater than 0 on this interval. Here in our reasoning, we make the connection between moving right and left depending on the sign of the velocity. So similarly, in part C, when is it moving to the left, the particle? Well, it's moving to the left on the interval from 3 to 7, and that's because v of t is less than 0 on this interval. Part D asks, where is the acceleration positive? Let's not make physical meaning of that just yet, but literally just answering the question, where is the acceleration positive? We talked about in the introduction that acceleration is the derivative of velocity. So essentially, by asking where is the acceleration positive, we want to know where the velocity's graph's derivative is positive, and that's where the velocity graph is increasing. See here, positive slope. The acceleration is positive. And we answer the question as t is an element of 4 to 6 because, now why is the acceleration positive? It's because the derivative of velocity is greater than 0 on this interval. And once again, our justification helps the reader to make the connection between acceleration and velocity with a derivative statement. Part E asks about when the particle is speeding up. Now, speed is an interesting one and often confused with acceleration. So we talked about if a particle is literally moving to the right, we say the velocity is positive. If the particle is moving to the left, we say that the velocity is negative. But what actually is acceleration? Well, think of acceleration as a pull. So if the particle is being pulled to the right, we'd say the acceleration is positive. If the particle is being pulled to the left, we would say the acceleration is negative. But don't think that because you're being pulled to the right, you're actually moving to the right. Suppose that the particle is actually moving in this direction, but suppose you're walking in this direction. Here's you, and you're walking that direction. But then you have me, here I am, I'm holding you back, trying to keep you from pulling, but you're pulling stronger than I am. So I am the acceleration pulling you to the right, where you're actually moving to the left. In that circumstance, you're going to slow down. So the only time that you speed up is when your velocity and acceleration are in the same direction. If you are moving to the right and being pulled to the right, well, you're going to speed up. And the same is true to the left. This is often recognized in our gravitational system. So you kick a ball up. On the way up, the velocity is positive because it's moving up. Meanwhile, this constant force of gravity is pulling it down. So on the way up, it's slowing down. But on the way back down, once it hits a zero velocity, it starts to come down. Now what happens as it comes down? Well, it's moving down and being pulled down by gravity, and hence speeding up. So to sum this all up, it's speeding up when the velocity and acceleration share the same sign. If I carefully analyze my graph, let's take a look where velocity is positive, where the particle's moving to the right. Well, here, velocity is not changing, so it's zero acceleration. Here, the acceleration is negative. So nowhere on that interval do velocity and acceleration share the same sign. Let's take a look when velocity is negative. Well, here, the velocity is negative because the graph is below the axis, but acceleration is also negative. So the particle is speeding up here. On this shaded purple interval here, the acceleration is positive while the velocity is negative, so the particle is slowing down, and the particle certainly is not speeding up here because acceleration is zero. So here's how we're going to write our answer. Particles speeding up on the element of 3 to 4. And this is because, now I want you to be real specific on this. We're going to say the general rule, which is v of t, and a of t, the velocity and acceleration, share the same sign. You certainly can say have the same sign, but let's just write it like this for the moment. So I want you to state the general statement. Velocity and acceleration share the same sign. But then I want you to follow that with very specific. So we're going to say v of t and a of t are both negative. In the event that they were both positive, you would say that. So we're negative on 3 to 4. So you give the general rule and then specifically. If the question asks for slowing down, you would say v of t and a of t have different signs. And then you would be specific what the signs were for each. We're going to move on to example 3. We're going to leave the evens for homework. So the velocity is defined as follows, and it is defined on the open interval -2 to 2. This is a technology question. The technology is required, so we will review some of those aspects. The concept here will be the same. In question 1, the velocity graph was given. Now that we are in question 3, the velocity graph has to be produced. Let's start by putting this into our calculator. So I know the function says v of t, but we're going to use y1 of x in your calculator. So you go to the y equals menu, and we're going to use x as a dummy variable. 8 plus 2, so we're going to use x instead of t, so it graphs it in traditional Cartesian plane, e to the x squared. Let's show you the syntax in case you're struggling to get that to be exactly what you want. We're going to say 8 plus 2x, that part's fine, minus e to the power of, now the parentheses will come up, and we'll say x to the power of 2. So that's exactly how you would type that one in. Okay, now before we graph that, let's change our window here to be descriptive of this. So x minimum -2, x maximum +2. I guess you can keep your y window -10 to 10, fairly standard, or -5 to 5. And then once you have the window set, you're ready to graph it. Now you do not have to show the graph, but I'm going to encourage you while you're still becoming familiar with this, I'm going to encourage you to graph it on your paper, draw the graph. So when we draw this graph, it should look something, it's not going to be perfect, but something along the lines of that. Let's remember that this is your velocity function, and the concepts relating the graph of velocity to words such as moving right and left will all deal with this. Now you'll see this would be great if I only knew the zeros. So what you're going to have to do is take a moment and find the zeros of this function using your calculator, and once we have those zeros, we'll be able to answer all the questions. It is also good practice that when you find the zeros, you write a blanket statement somewhere on your paper just denoting what the zeros are. So for instance, I will say v of t equals 0 at, now I've got to put the work into finding those zeros, and once you find the zeros, you will learn that they are at t equals -1.299, also at t equals 1.552. So I haven't even started answering questions, but this helps me to identify the zeros, and it also can count as justification. We never want to forget to let the reader know that we have found the zeros, and we write it like this to make that happen. Let's answer the questions. At what time on the interval -2 to 2 is the particle standing still? Well, we just learned about this. So we're going to say t equals, a little bit redundant, doesn't hurt that I wrote this somewhere else just for reference, but t equals -1.299 or t equals 1.552, and that is because v of t equals 0 at these t values. We have an answer and a justification. Part B, when is the particle moving to the right? Well, let's go over here. I like to make this good practice. V of t is greater than 0 above. V of t is less than 0 below the axis. Okay, so when is the particle moving to the right? Well, that's when t is an element of -1.299 and 1.552. And that's because here v of t is greater than 0 on this interval. On what interval is it moving to the left? So yes, you got the concept when it's below the axis, but let's make sure we have the notation down correctly. We can't equal -2 because in our beginning it's not defined at -2. I also want to address the fact that some students say you can't have negative time. Well, actually you can. Time is very arbitrary and in indexes. So if at this very instant time is 0, then when the video started, it was negative 10 minutes ago. So it's all in reference. So negative 2 could mean negative 2 minutes ago. At any rate, t is an element of negative 2, not inclusive, all the way up to negative 1.299, in union with 1.552 all the way to the other endpoint, 2 not inclusive. And this is because v of t is less than 0 on this interval. Now for part D, on what interval is the acceleration positive? First, let's get a visual of that. Acceleration positive if the slope of velocity is positive. So it's clearly going to be on this interval here. Now there's going to be a very specific way that I'd like you to go about answering this. The AP supports this technique. Instead of eyeballing or even figuring out a max to determine this interval, the idea here is we are going to graph the acceleration. In order to do that, we're going to go to our home screen in the calculator. In the home screen, we're going to take the derivative of what we have as y1 of x with respect to x. Now that's going to output, when you press enter, an answer. You're going to highlight the answer, and then you're going to go to your y menu and define y2 to be pasting of the answer. That will allow you to graph the derivative of velocity. In other words, that's going to allow you to graph the acceleration. Using the same window settings, the acceleration will look something like this. It'll come down and then go like that. This is the acceleration graph, y equals a of t. We can see that when it's above, a of t is greater than 0, and when it's below the axis, a of t is less than 0. We'll use the calculator in the same way to find the 0 of the acceleration graph, and when you do that, maybe take a minute to do it. When you do that, it'll come out to be 0.653, and we'll use that to answer the question. On what interval is the acceleration positive? T is an element of negative 2 to 0.653, and again that's because v prime of t was greater than 0 on this interval. I've been asked the question, well, can't I justify with a of t is greater than 0, or the a of t graph is greater than 0? The problem with that is it's asking where is the acceleration positive and why. It would be sort of weird to say acceleration is positive on this interval because acceleration is positive on this interval. So by writing it in the white derivative way, we're able to illustrate the concept. Now to answer the question, where is the particle getting slower? We're going to introduce this thing which I've coined the no point number line. It's called no point number line because on the AP exam it doesn't count for any points. You're not given any points, nor are you losing any points. But it certainly is a great schematic to help understand and answer the question. This first axis that I've drawn here is the t-axis. I'm going to identify the zeros that I found above here. So I'll label them, let's say, here and here. And one was at negative 1.299, and the other was at 1.552. Now what I'm going to do in this schematic is indicate what the sign was. Remember here, we were below the t-axis, so velocity was negative on that interval. Then between the two zeros, the velocity was positive, so I'll indicate positive for velocity. And then once we got past 1.552, the velocity went back to negative. So that describes the sign of velocity. So the next t-axis that I have drawn is to represent that of the acceleration, and we had a 0 at 0.653. We're rounding to 3 decimal places, of course. Now we're going to indicate the sign of the acceleration. Well, to the left of that 0, the acceleration was positive, and then after that the acceleration was negative. And I hope you see how this is going to be helpful. If I break this down like this into the different zeros, I can see the category where velocity is positive and where acceleration is positive, so on and so forth. Now we'll answer the question, where's the particle getting slower? So the particle is getting slower on the interval -2 to -1.299 in union with 0.653 to 1.552. And that is because, we'll start with the general, that V of t and A of t have opposite signs. V of t and A of t have opposite signs on this interval. That is not enough to just say the general. I want you to be very specific, and sometimes people hate me because of this. I'm sorry, but I want you to be very specific. We're going to say, I'll use a little like bullet or such, on the interval -2 to -1.299, we'll say that V of t was less than 0 and A of t was greater than 0. Please make sure you put these bullets and be very specific. Also, we're going to say on the interval 0.653 to 1.552, V of t this time is positive and A of t is negative. Make sure you say both of these. It's not okay to just say this. You want to make the connection, opposite signs for slowing down, or same signs for speeding up, and then you want to give the specifics. Both are required. Part F. This is more of a technology thing. The question wants to know what are the velocity and acceleration at time t equals 0. Well, we already have this defined in our calculator. This is the velocity, is y1, and the acceleration was y2. So if I want to find the velocity at time 0, y1, actually literally in the home screen, type in y, then type in the number 1, followed by parenthesis, and then you can type in 0, and that comes out to be 7. So V of 0 equals 7. Also in the home screen, if we say y2 of 0, it'll tell us that the answer is 2. The acceleration at 0 equals 2. For the moment, we're going to ignore the units. Okay, last example, number 5. Again, the evens are going to be homework. In this problem, a function is defined. It is a position function, and it is defined on the interval -5 to 5, not inclusive. This is non-calculator, so everything must be done by hand. In fact, you might want to try to do the whole thing before watching this video. Maybe press pause now and then follow the solutions. Here we go. On what time interval is the particle standing still? Well, V of t, we know, is the derivative of position. And if I take the derivative of position, t squared minus t minus 2. And I'm going to set that equal to 0. And if I simply factor this, t minus 2, t plus 1 equals 0, I get that t equals 2 or -1. Suppose I left my answer just like this. I did nothing else. There are two parts. One, you have to answer the question, and one, you have to justify. Is it okay to leave the question just like this? And the answer is yes, because here is the answer. And why is that true? It's because V of t equals 0, and I've shown that, so no need to write any more. The justification came first, followed by the answer. On what interval is the particle moving to the right? Justify. I'm going to continue with this no point number line idea. So this is the t. I'm going to identify the zeros, which were -1, +2, and I have to determine the sign of velocity on each of these intervals. So velocity. Now, one of the things we can do is plug in numbers on the particular interval. So for instance, let's suppose I plugged in a number between -1 and 2, let's say 0. Well, this quantity, if I plug in 0, is negative. This quantity, if I plug in 0, is positive, and the product would be negative, so the velocity on this interval is negative. Let's check the sign when t is greater than 2, let's say 3. If I plug in 3 here, it's positive. If I plug in 3 here, it's positive, so the velocity will be positive on that interval. For -2, this will be negative. -2, this will be negative. The product is positive. So to answer the question, t is moving to the right on the interval of -5 to -1 in union with 2 to 5 because v of t is greater than 0 on this interval. In part C, it's moving to the left on the interval -1 to 2 because the velocity is negative on this interval. Part D, on what interval is the acceleration positive? Let's find the acceleration. So acceleration is the derivative of velocity, or also known as the second derivative of position. So we'll take this derivative and we get 2t minus 1. And we want to know where it's positive. So first I'm going to set it equal to 0, and that's going to give me t equals 1/2. If I employ this no point number line business, then I locate a half, I label this t, and I figure out the sign of a. Well, if I plug in a number to the right of 1/2, I'm going to get positive numbers. If I plug it to the left of 1/2, I'm going to get negative answers. So I can answer the question that t is an element of 1/2 to 5 because v prime of t is greater than 0 on this interval. To find the interval in which the particle is speeding up, I put the two no point number lines side by side. Remember, you don't have to do the no point number line. It's worth no points, but it does help. This helps you to see the interval. We want to know where the particle is speeding up, so we're going to say t is an element of -1 to 1/2 in union with 2 to 5. And that's because v of t and a of t share the same sign on this interval. That's the general part, and now the annoying specific part. And we write these on -1 to 1/2. V and A are both negative. On 2 to 5, V and A are both positive, answering the question in its entirety. Finally, in part G, it's just a little bit of arithmetic. What is the position at 1? Well, you plug 1 into the position function. 1/3 minus 1/2 minus 2 plus 3. Make a common denominator. Simplify 5/6. The velocity at 1 is going to be 1 squared minus 1 minus 2. We plug that into the velocity function. -2 is that response. Acceleration, 2 times 1 minus 1 equals 1. Again, we're going to keep this unitless for a while just to get the idea of the concept.